Hello and welcome to the Quantizer. Today we're going to talk about pulse width modulation and using that to create an analog signal. So basically taking a digital signal and turning it into an analog signal. And we're doing that because we're working on this Puppy Patrol project and where we want to be able to drive an audio circuit so that we can play a siren if we see the dogs on the couch and say, hey, you're not allowed to be there. And so what we're going to do is taking the Arduino, which can only output a digital signal, and we're going to pulse width modulate that to ultimately create an analog signal that drives the speaker. And how we're going to do that is we're going to send in that pulse width modulated signal into this low pass filter. And what that will do is kind of smooth that out by charging up this capacitor and resisting that change in voltage, and it will create this kind of jaggedy sine wave at the frequency we're looking for. That will be at a DC offset, meaning it'll have a DC value. It won't be alternating between positive and negative, but it'll be alternating between a lower and a higher positive value. So that's why we put this other capacitor in here, is to block that DC and to bring that signal back around the zero, or to the zero rather, and so that it will alternate between a positive and negative value, which is what we need to ultimately drive the speaker. And then this resistor here to act like a voltage divider so that we can change the volume. So this resistor is used to adjust the volume by, if it's pointed all the way down at the bottom, then it's connected to ground, so it's 0. And if it's all the way at the top, it's the full signal here. And if it's in the middle, it's half of what the input signal into it here is. And that's how we'll control the volume or set the volume for our project. And so we have simulated this in KiCad, which uses NGSpice in the background. And what we've done is, we had a difficult time actually generating the pulse width modulated signal, so we created our own element. And if you want to know more about that, we're going to be writing up a blog. But basically, we used NGSpice, or it uses NGSpice, so we had to read the manual and figure a bunch of stuff out. And just to see it really quickly, you'll see that we have, this is it. It's a sub-circuit that we've put in there that will take in two parameters of a frequency and a sample rate. And it does that to set two internal inputs, I guess. And what they are is this first one that creates a clock, right? And that's happening right here. And then this one that creates the control signal, which is happening right here. So basically we're saying like, hey, let's create a pulse, which is just a square wave, and let's have it be at the frequency times the sample rate times 2. And this is just so that we can set the frequency and the sample rate so that the clock happens X amount of times per input signal, and this input signal is just a sine wave at that frequency. And so it will sample that sine wave, for this in this example 10 times per cycle, and then produce a pulse in the output. And that's going to be driven by this one shot right here, which will take that sampled voltage and create a pulse that is proportional to that width. And we set that right here by this array, saying, hey, if you're at negative 5 volts, then give me a 0 width length, and if you're at 5 volts, then give me at a 1 over this equation, which is pretty much a full cycle's pulse width. And that's how, and anything in between, it's this linear selection between those two, and that's how we'll get a pulse width modulated output. And we'll put this up there so you have access to it. There should be links down in the description to both our blog, or you can go to www.thequantizer.com, and you should be able to find this there as well, and we'll link to it as well. So we have that as our sub-circuit in here, and we created this symbol. And these two outputs right here, they're not necessary. We just have them so that we can sample that signal, or that control line and the clock, and just for demo purposes, right? If you were to put this out yourself, you just need to connect the ground and or to clear the ground and the output, and you can modify the frequency and sample rate by adjusting these values. But enough of that. Let's actually show what happens. So we're going to run this simulation. If you don't know how to get there, you say Tools, Simulator. It'll bring up this window, and then we'll run the simulation, and then we'll probe. We'll start by probing the output here. And so this is what gets outputted by our PWM circuit. And it may look a little strange right now, but if we probe the signal and then also the clock, it'll make more sense. So on the, I'm going to take this one off and get a different color because that blue is hard to see. So yeah, we'll go with yellow so we can get a better look here. So if we see at the negative clock edge, the negative edge of the clock right here, it's going to sample this voltage value and it's going to say, okay, you're at negative 2.4, so I'm going to generate, you know, a smaller pulse. And then again, it's going to sample right here and say, oh, you're at a much higher value, I'm going to generate a higher pulse. And then right here, it's going to sample, and it's almost at the peak value, so it's almost going to generate a full clock cycles pulse. And then it's going to keep doing that, and you'll see how, depending on where you're at, we have this pulse width being modulated by the voltage value of our input signal. And so we just change the frequency of this, and we will get a different pulse width modulated output. And that's how we built that circuit. So, you know, it works, and you can use it, so you don't have to go through what we did, which was to create it ourselves, because there was not a simple block to do that. Anyways, let's talk about the output of this. So the first one here, like we said, is going to try to take that, let's take these other signals out of here first. It's going to try to take that, that pulse width modulated signal and create kind of a sine wave looking signal right here. And that's what it's doing. And so let's see if we can get a better view. There we go. So what's happening is let's bring on the output of this as well in the picture so you can kind of see it. What's happening is it will, when the pulse goes high, the capacitor is going to charge up, right? This capacitor right here is going to charge up. And then whenever it goes low, it's going to discharge, and then it's going to charge up from the high things and discharge, and charge up and discharge, charge and discharge. And so we selected these values so that it will not saturate or charge too quickly or too slowly to actually get an output. And another thing to keep in mind is when you have a low pass filter like this, it's a low pass filter. So what it will pass lower frequency signals and block or attenuate higher frequency signals. And so it's important to get your calculation so that it's in between, you know, getting a smoother charge cycle, right? And not filtering out your frequency of interest. In our case, we're dealing with audio. So our frequencies of interest are between 20 hertz and 20 kilohertz. And just because of the limitations of the Arduino, we decided to go with a 250 hertz pulse or frequency and a 500 hertz frequency. So our range is between 250 hertz and 500 hertz. That's what we were interested in. And so to give you an example of how we can select some of these values, I'm going to go with just considering one factor, and that's the smoothness of the wave. So in order to do that, what we could do is just modify this resistor right here to change the RC time constant. And if I was to use a 1 kilo ohm resistor instead, we will see what the output does, and you will notice that it's a much rougher signal, right? And so you go, okay, well, let's go in the opposite direction. Let's get a 10 kilo ohms resistor. I think I said hertz earlier, but yeah, 10 kilo ohms resistor. And you'll see that this is a much smoother signal, right? You could keep going up, but you start to run into a problem where you'll notice that this signal was smaller than the earlier one because this low pass filter is going to filter out or attenuate or lessen the peak to peak voltage value of higher frequency signals. So you have a trade-off you have to deal with. And what we did is we kind of said, okay, well, what's really important to us is that we don't have two different volumes coming out for the 500 hertz and the 250 hertz. So we really want that to be, them to be close to the same attenuation value. So we had to push the curve pretty much as far as we could without messing with this too bad. So in this case, we have a 10 kilohertz and 100 nanofarads capacitor, and what that will give us is a 160 hertz knee frequency. So that's at the 3 dB point. So that's when it starts to really attenuate a lot, right? And so we said, okay, well, that's too much, right? And we know that we wanted to bring it above or around 500 hertz because that's our top frequency. And so when we used a 3.3 kilohertz or kilo ohm resistor, we were able to get something that was really close to 500. So it will attenuate us a little bit at our higher frequency, but not too much. And so it was kind of a good balance between a smooth output and not having an audio, like a noticeable difference in the two frequencies that get output here. So that's why we picked those two values. And that's what to keep in mind when you're dealing with a low pass filter circuit like that. So we had that, and then we brought it to a decoupling capacitor right here. And the purpose of this is you'll see that this output is going around in our current example 2.4 volts. So it's going between this higher positive voltage and this lower positive voltage, but we want that output to actually circle or to oscillate around 0. And so in order to oscillate around 0, we put this decoupling capacitor in here. Let me modify this back to the values we're looking for, 250, and then we want this at 3.3 kilo ohms. So let's rerun this simulation. And I said, okay, not as smooth, but we don't have nearly as much attenuation as we did before, so that's good. And now we're going to probe after this bypass capacitor, and you'll see that now we have the same wave just oscillating around 0 instead, which is what we want. So we wanted that, and we also wanted to select, to have a volume selection. So right here, this is simulating taking the potentiometer that we put in there, which is just a resistor. You can vary what the middle output's resistance is at, whether you have it all the way up at the input, somewhere in the middle, or all the way down at ground, which would be 0 volts, right? So this one's right at the middle between 5K and 5K because it's a 10 ohm potentiometer that we're using. And so you'll see here that this should be half what the input is, and that's what you got. Same wave, just half, and that's how we're going to control the volume with it. And so that's nice. But again, when we built this circuit, we use this to circle around 0. We just select volume. This creates a high pass filter, which is the opposite of this. And so we have a similar problem, but not as bad, which is where we said, okay, we just want to make sure all the higher frequency stuff gets through, because we want to block the DC value, which is a low frequency, which is actually at 0 hertz is DC. So what we did when we calculated our resistance and capacitance value is we pushed our output all the way as far to the left side of this graph to 1 hertz was reasonable. And so that gave us, we started with a 10 kilo ohm potentiometer because they were very available and we had some. And then we just got a capacitance value that we had and used that. And so this gives us a high pass frequency that pass things above 3.39 hertz, because again, we don't really want it to act like a high pass filter. It just does because of the other characteristics of the circuit that we wanted to have, which is volume control and to use a decoupling capacitor. Okay, so that's nice. And to show you some of what it looks like with the two different frequencies, like we talked about, how if you select these capacitance and resistance values in a way where you get a smoother output wave but more attenuation, you'll see what happens. So we're going to probe, we're going to remove all of these things, and we're just going to probe what the what it looks like on the output. And you'll see that with our current setup, they're pretty close. So the higher frequency one, which is in blue, is attenuated a little bit more than the green one is. And I'm actually going to take the blue off because again, that's hard to see the blue color. Yellow. So you'll see that, yeah, you'll see that the green is a little bit higher than the yellow is, but it's not too much, and the waves are, they're okay, right? Let's look at one of the higher frequency waves. It looks okay. You could definitely, it looks like a sine wave. And what would happen though, if we decided to go with something that would give us a smoother value, you will see the negative that shows up in that situation. So if we run the simulation again, and now let's probe both of these guys, you'll see as we zoom out that the higher frequency value is now at a noticeable, in fact in the audio you'll be able to tell, maybe not a whole bunch, but you'll be able to tell that they're at different volume levels just because of the filter characteristics in our circuit. So that's why we chose the values we chose. You can choose whatever you need to choose for whatever project you're dealing with. Because of the way that ours was set up and the characteristics that we wanted to get out of our circuits, these were the values we ended up choosing. And so now I'm just going to put these back in here and rerun the simulation so you can see that they're much closer in peak-to-peak values. So now we're going to show you what it looks like when you actually build a circuit. So we did. I'm going to bring up my waveforms software right here. What I have is this thing called a Analog Discovery 2 from Digilent. They're really useful for things like, I guess, below 25 megahertz. I think that, or yeah, 25 megahertz I think is the top end of what it can do. But anything that we're dealing with right here, I mean, this is just great for, because it's got like an entire electronics lab in one, where we have all these tools that we can use. And so right now we're going to use this the oscilloscope and the waveform generator that we have plugged up. So this waveform generator is plugged with the input of our circuit, and these are plugged in to measure the input on the yellow line here and to measure the output on the blue line here. So if we start that and we start this, we'll be able to see, let's hit the trigger set, we'll be able to see the inputs and outputs. So we're inputting this square wave and we're outputting this sine wave thing right here. What's interesting to note too is that that just having, I guess, a resolution of one pulse per cycle actually gives a pretty decent sine wave with less noise on it. You could only make a sine wave that way, but yeah, it works pretty well. So anyways, we'll just show you what happens with the circuit, because we designed it, remember, to operate between 250. So there's 200 hertz, and here's 500 hertz, and you can see they're roughly the same peak to peak value. So we get what we're looking for here. But if we go beyond that, if we go above 500 hertz, which will start to really decay pretty quickly for our low pass filter, you'll see that the output starts to shrink. So if you try to get too high of a frequency through there, it's going to actually, the volume's just going to go down, right? So this thing was designed to operate between the two frequencies that we cared to use for our project. And so that's what it looks like if you just send in a square wave. And so now I actually have the code in the Arduino hooked up here. I'm going to plug the Arduino in so we can start using that as the output to show you what some of those signals look like if we have more resolution in here. So this one right here is, I believe it is 8 points of resolution per wave, and I think it's doing a 500 hertz signal. But we can check that out. Let's set the trigger up here. So if we zoom in here and then we take our measurement, which I'll do this one. Let's pause it real quick so it doesn't jump around. Let's go from this peak to that peak. Oh, whoops. That's good enough. Yeah, that's about, I guess it's 528 hertz, what it's saying, but yeah, it's about 500 hertz. So that's what we have right here, and it looks, it doesn't look too bad. It's definitely got some sine wave characteristics here, but what I think is interesting though, and just so you know, this is what it looks like. This is what our input signal is. So we have this pulse width modulated signal to help us generate this deal, which you can see is when it goes on, it charges up. When it goes off, it discharges, charge, discharge, charge, discharge, charge, discharge. So that's kind of how you can make that. But you could also just use a don't really modulate the pulse width and just send pulses in and use that same circuit, and I think you get pretty smooth, pretty decent results. So let's show you what that looks like. So we're going to, instead of using this sine 8 array, we're going to use a 2-bit version of it, and we'll comment this out. This is just to help us do the math in here, which we said it has an array length of 2, because there's 2 things in here, and there's 1 bit per message. And that's what we're going to do. And then we also have to adjust what we've decided to call our high frequency. So let's see, at 500 hertz, so with this one we're going to need 16,000. That's just controlling how often we go into, whoops, we got to change that to 2. That's just controlling how often we're calling this ISR, or this service, this interrupt right here, this interrupt service request, I believe what ISR stands for. Anyways, let's go back over here. Let's run the output, and you'll see that it's a decent one where we just have 1 charge and discharge cycle for this deal. And let's see what frequency we have. It's about 500 hertz. So another thing we'd like to show you is the frequency response of the circuit that we built. And how we're going to do that is with the network analyzer that's part of the analog discovery. And what we have is the waveform connected to the input of the circuit and the oscilloscope connected to the output of the circuit. That way we can send in an input and measure the response. We're going to go between 50 hertz and 1 megahertz, and we have it set to voltage peak is the output. We're going to run that. A lot of times when you see plots like this, they'll be in dB, but we've decided to do it in voltage peak because I think it's easier to read. So what we have here is the frequency response. You'll see as we go to the frequency of 250, which is one of the ones we're interested in, we get pretty much near the top of this curve, and so that's nice. We'll get most of that output. And then if you go over to 500 hertz, you'll see that we're over here, which we're still pretty high up there, and this is where the output was for that frequency. And so the 500 hertz will be slightly attenuated compared to the 250 hertz. So one way we can improve this circuit is by using different values for in the high and low pass filter to shift this over to the right. That way, like if the 250 was here and the 500 was here, they would come out at the same volume for those two different frequencies on this curve. Right. So yeah, so that's how you can make one of these things happen. So if you have any questions or comments, feel free to put them down there, and don't forget to like and subscribe, and let us know things you might want for us to talk about. And you can also visit our blog at www.thequantizer.com. Thanks, and have a nice day.